Okay, Katere, if you want, you can start.
Okay. The subject of our research is modeling synthetic catalog of earthquake rupture in a complex interacting fault system. The first question is, why do we need synthetic earthquake catalogs and why don't we use real ones? There are two main reasons for that. The first is the historical record of seismicity is too short to enable us to make a firm conclusion about the recurrence time of large earthquake and possible clustering in time and space. As we can see in the right picture, these are the recorded earthquake for the years 1900 to 2017. This number is too few to actually make a firm conclusion. And the second reason is, although paleoseismic studies are able to extend the records for some specific regions, but they are actually through the process is too slow and subjected to uncertainty. The ultimate purpose of this study is to determine how hazard is modified by elastic interaction of events in complex fault systems and to examine the synthetic seismicity for unusual behavior before large events that might be observed in the real world. For example, in the regions with a low to moderate seismicity rate, sometimes a large earthquake happens. The two famous ones are New Madrid earthquake and Charleston earthquake in the eastern part of the America. And the recent example can be Kaikoura earthquake in New Zealand, that in that earthquake, some part of the fault system ruptures that never have been expected and actually not predicted. When this kind of earthquake happens, usually cause a catastrophic number of casualty and loss. By actually making some synthetic earthquake catalogs, we can predict the probability of accidents of this kind of earthquake and prevent this kind of happening. Because this kind of event happened in low to moderate seismicity, the reliability and strength of the building are too low to tolerate this kind of earthquakes. There are two methods for synthesizing earthquake catalogs. The first one is based on the past earthquake. This was the subject of my master degree thesis. We can see the comparison between synthetic epicenters and real epicenters. The distribution is somehow the same and the magnitude also are the same. This is for the Zagros region in Iran, and the number just decreased because it is the aftershocks catalog. The second method, which is the this research subject, multi-cycle earthquake rupture simulators that generate long sequence of earthquakes along predefined fault geometries for statistical analysis of earthquake reoccurrence and related rupture characteristics. It also have to actually featured with some characteristics. It should work with complex non-planar fault systems and heterogeneous models of fault strength. It should incorporate elastic signal propagation velocity and distinguish between stable, conditionally stable and unstable part of the fault, and also include post-seismic relaxation and after sleep. The process is somehow an iterative process that is between applying tectonic loads to the elements and test if the element fail or not. I mean, the shear stress exceed the strength of the element or not. The first step is modeling the earthquake geometry. We can see in the first picture that two rectangular fault surface join each other. And in the second step, we mesh this surface into triangular small subregions. And then by superposition of a meshed faults with 2D random field, we create a rough fault geometries. And in the last step, we have to observe the stress change in element J due to the slip in element I. Most of the studies were meant to model seismicity in general sense, but some models specific faults. For example, Benzion and Rice research developed a model that represents San Andreas fault near Parkville, where a series of periodic magnitude 6 events have occurred. They suggested that models with discrete area of uniform slip are perhaps a better representation of the mechanical and geometrical complexity of real faults than continuum limit models. Also, Robinson and Raphael developed realistic three-dimensional model that represent the system faults near Wellington in New Zealand. In general, complex and perhaps chaotic behavior is observed in many synthetic seismicity models. We are in the first step of our research, which is modeling the fault geometry and behavior. The challenges that we are faced are selecting the faults that make the model according to that, and selecting the number and size of triangular elements that be accurate and optimize the calculations. The first ideas to overcome this challenge is to start with simple general fault and then assign the characteristic of active faults in central Apennines, Italy. Also, the results from the research of John, Micah, and Rachel can be used in this step of the project. We can see the this is active fault in the central Apennines, Italy, that we have all the characteristics, this activity rate, and the geometry of the fault available. So we use this fault system to our model. And for the second challenge, we assumed a mesh with relatively large size and then decrease the number to observe the changes in the results. In this project, I will spend 6 months in Germany for modeling seismic column stress change and fluid migration and viscoelasticity, and also 4 months in Trieste under supervision of Professor Peruzza to analyze sensitivity on input variability and uncertainty. I mean, we should actually test how these input from synthetic earthquake catalogs can change the results in hazard maps and hazard analysis. And this is the end of the presentation.
Okay, thanks, Katerina. Any questions? Yes, Alessandro.
No, it wasn't a question. Sorry, it was.
All right.
Clapping.
Okay, so so it's a full 3D model in that case. So that you're going to use, is that right? So or not? It's not clear because you're showing at the beginning. You're showing faults that are discretized along the fault itself, and then when you show maps, it's it's not clear to me that you will use a 3D model or a 2D model only.
It will be a 3D model.
It's really a 3D, yeah. Okay.
Yes, there are actually the non-planar faults I mentioned because it should be And actually, the roughness of the fault is considered in this project.
And I wonder, I mean, does this type of model generate aftershocks, or what conditions do you need to generate aftershocks?
Do you mean the aftershocks?
Yeah.
Could you please repeat the question?
I mean, do this model type of models generate aftershocks after, like, you have a large rupture? So how do you model aftershocks? Because normally they tend to occur on, either, I mean, the main fault itself, if there are, patches of, positive stress increase, or mostly on small secondary faults that you don't really model. So I'm wondering if you can generate aftershocks and then NMO is low, and so what elements will you need to generate this, or maybe you don't care, you want to have only the main shocks over long time scales. It's not clear to me.
Actually, we are planning just the main shocks, but actually it's a different phase of the seismic cycle is considered in the project. Post-seismic relaxation and after sleeps also is included in the considering the model.
David, if I can add something about the,
Sure.
studying the hazard related to aftershock sequences is not the purpose. And
Right.
I don't think that the code takes into account aftershock sequences, because the smallest event that that can be generated is basically equal to the smallest size of element that is in the 3D model, so in the triangular elements mesh. But for cat array project, we are going to focus mostly on main shocks and events that play a big role in, let's say, in the PSAJ age A. So not aftershocks are not going to take into account.
Okay.
But there's going to be the part with fault interactions and element interactions. So.
Okay. And maybe just a last question, but it's some time ahead of you, Katere. But you mentioned fluid migration, so that's going to depend strongly on the permeability, and which is normally unknown. So I don't know what you're going to do with this.
And you made the parts in the Germany, 6 months in Germany.
Yes. You haven't thought about it yet, or I don't know.
No, we haven't thought about it.
Okay.
David, sorry if I'm adding.
Yeah,
this is like some kind. I wouldn't say naive, but that would be a very, very important, very significant implementation that we will try to add. Obviously, with all the uncertainties connected, the initial idea was to implement poroelasticity and so earthquake triggering by poroelastic effect due to fluid diffusion. So in that line, but obviously the model is not going to be so complex. So we have to, think about that.
No, yeah. I mean, it's possible that the fluids, play a major role, especially, in central Italy. But I mean, the issue is really to so poroelasticity is good, but then it's controlled by the permeability, and then so there's something that I don't know how you're going to control. But yeah, especially since permeability very likely change over time, during the sequence. So I don't know. But interesting. Okay.
Yeah. Let's see. I mean, in general, fluid, they're more, let's say, the evolution of aftershock sequences are much more related to fluid migration than, for example, triggering of, let's say, main shocks.
Yes,
but
but
yeah, that was also an idea, try to implement something that can be useful for our purposes. But let's see.
Okay. Any other question? Anybody? Nope. Okay, thank you, Katere. Right. So now I can't remember. So yeah, Jarod is not there. So who was taking his place? I can't remember actually. Oh, Julian, is that you? Yeah.
Yes.
Yeah,
I'm
sorry.
going to share my screen.
Yeah.
Hola a todos. Can you hear me?
Yes.
Let me. It say host disable participant screen sharing. So I cannot share for now.
You cannot share?
I
Oh,
made
yes.
you co-host now, so you should be able to.
Yeah.
Okay. No, I can. So let me know if you're watching my screen. So hello everybody again. So I am the DC11. I am in the place of Jared today. So with John, we were planning to have a Colombian session the next session, but it was impossible for now. So my project is about the assessment of the impact of advanced seismic hazard modeling approaches in earthquake risk. So if you remember in France, okay, we talk about different seismic approaches, but now we are starting with the side effects. So the why, let me do a little introduction. So this is our 11 projects, no, and the projects are most related with the hazard-oriented component, no, since the multidisciplinarity from geology, geomorphology, different numerical and physics-based models, no, that the main purpose is to establish and model a seismic source. And this is me working in the risk component. But if we see the link between the hazard and the risk, so one of the main links between both is the ground motion, the ground motion modeling. So for this, there is two different things we have to take account, no? And the attenuation and the effect of the site conditions. So about the ground motion models or the ground motion prediction equations, there are several in the literature, and they are centered principally in the attenuation, but they include some simplified models for the side effects or the effect of the soft soils, no, in the shaking. But our question is, okay, ground motion models are principally related to attenuation, but is the side effects from the ground motion enough, or what kind of uncertainty it has? So for this, in this presentation, I have three different topics we are working in. I'm going to present the side effects estimation approaches we are using, the case studies we are beginning to work, and an example with the Colombian city, Popayan, and our preliminary results. So about the side effects estimation approaches we are using. So this is a traditional example. So here we have the earthquake source, now the seismic waves, propagation in a path, and then the seismic waves first are in the bedrock. We can find the bedrock buried above the ground, or we can have outcropping bedrock exposed in the surface, and then we have the soils. So the side effects have different phenomena. Now, for example, the effects of the buried soil layers then have amplification and some de-amplifications in some terms about the shaking. We have topographic effects, not just the soil behind our point of study is altering the waves, but also the geoforms in the surface, even if we have rock sites. And we have also lateral heterogeneities. So we have different phenomena affecting the seismic waves from the bedrock to the ground surface. So here, okay, many of the cities are located over deep sedimentary basins, because okay, our cities are close to big water components like rivers and valleys. So, and because the sedimentary basins are floods, so at many reasons that what we have the cities in the sedimentary basins. And we are often using the BS30 as a good proxy. And the BS30 is just the average value of the BS wave in the most upper 30 meters. But in some cases, for example, I have here a BS profile in Bogota. Let's think about the first 30 meters. Okay, in the first 30 meters, we have a BS value around 200 meters over seconds. But for this profile, a BS value that we can consider rock is about 600 meters in depth or 700 meters in depth. And sometimes the people is modeling this kind of sedimentary basins with the first 30 meters. So just an analogy is that if we have the Burj Khalifa building that is around 800 meters in height, probably we are not going to design that building taking account just the first 40 meters. So we are neglecting in some cases up to the 90% of the soils. So we have to see the impact of these methodologies. As expected, the first approach we are using here is the side terms of the ground motion models. So we have the ground motion models that let us calculate the shaking and intensity measure, for example, spectral acceleration, given a rupture and a site. And they include, as I told you before, the effect of the site of the soil. But in many cases, it's very simplified approach using some proxies as the BS30. And here I have an example. Here we have three different ground motion models and three different site conditions. And we can see, for example, if we see the continuous lines, the continuous lines are amplifications from different models with the same BS30 values. So for the same condition of soils, we have different, very different values of the amplifications. Other approaches, okay, that was our first, but we can use other approaches. So probably not exactly from the ground motion models, but we can use the ground motion models in order to calculate the shake in a rock site, and then we can use other amplification functions. So, for example, we are using the amplification factor from the seismic codes. So we are using some old codes from the 80s or 70s, that are very common factors, and they are just like a constant value of the amplification. So it's really easy to design buildings, but probably easy is not the correct always. And we are using also the amplification factors from the classical codes from the 2000s. So in this case, we have some factors, a little bit more complex with soil categories based in BS30. And in this case, as we can see, these factors consider the nonlinear behavior of the soil. So for different level of shaking, the soil has nonlinear behavior and is decreasing the value in the amplification in some cases. Okay, we have the ground motion models, we have the amplification from the seismic codes, and we have another approaches. So for example, we have some amplification factors from ground motion data-driven functions. So for example, here we have the amplification factors from strong motion data sets. So for example, we have this paper from Seihan and Stewart that is a really famous paper in the amplification functions world. So they calculate amplification functions using the NGA West 2 database, considering linear and nonlinear behavior. And we also have that is a global dataset, but we also have some similar methodologies using strong motion datasets, but using just regional datasets. In this case, it was from Northern South America because we are working a little bit with Colombian cities. So it's very interesting just not just to see the impact of different methodologies, but also the different scales. No, we have global models and regional models. So up to here, we have 6 different possibilities. So it sounds like not many, but we have to remember, okay, we are using methodologies principally based in BS30. So what about the BS30? What BS30 we are going to use? No? So we have different proxies. We have, for example, the global models based on a slope. We have the model of the USGS. No, that is just a correlation between the BS30 and the slope. We have national models based on direct measurements and the slope that in some cases have better accuracy. And we have also, for sure, extensive measurements. No, in this case, we can use geotechnically and geophysical exploration in order to not use a model, a simplified model. So at the end, we have 18 different possibilities as side effects approaches. But what is the real value? No, we are going to compare the different approaches in terms of risk, but we have to define a target value. So we don't have 18, we have 19. No, in this case, the reality that we are going to define as a target is the amplification functions from the seismic zonation studies. So this is a zonation study. So for example, is different zones with different geotechnical and geophysical properties, but with a seismic behavior that is similar. And each of the zones has some amplification functions, including the nonlinear effects. So we can use that kind of studies that use modeling and real data and a lot of things in order to calculate the best amplification functions. So at the end, we have 19 possibilities, and also we can do another one because we have to compare what happens if we don't consider amplification. So as case studies, okay, we are going to use the 20 possibilities, but we need data in order to work with. So for example, in Colombia, we have many microzonation studies because they have to do by law, okay? So they are mandatory, but not all the cities have this kind of cities, that kind of studies. And we are using for now 5 different cities. Why is it important to have different cities? Okay, we are testing the impact of different approaches. And if we are testing the difference in approaches, we need a big abacus of possibilities. No? So we selected 5 different cities in terms of the geology or the predominant soils they have. They have different population, they have different hazard level, no seismic hazard level in rock, and they have different hazard predominant tectonical environment. So finally, one example that is what we are working in. We are working in the first city in Popayán, that is just Cordillera, is a really important event in the past because in 1983, there was a earthquake, no, magnitude 5.6 more or less, and they destroyed a big part of the city, and it's too important. For example, Fernando Otero, the Colombian painter, has a really famous painting about the earthquake. So here you can see some screenshot about that paint. So about Popayan, we have the soil component. So for example here, we can see the difference between the VS30 measurements, from the microzonation studies, and we can see the big difference with the national models and the global models. So just in terms of VS30, the difference in some cases are huge. And remember, in the amplification functions world, the difference can be bigger. Here we can see, okay, in this case, as you can see, the national VS30 model looks similar to the VS30 measurements, is what I hoped, no? But it has, okay, a big uncertainty too. And the global model is not the best option, but we have to compare all. And we have also the microzonation studies for this city with volcanic soils. And we performed a preliminary losses estimation. So we took the exposure model from a study from the Geological Survey in 2020, and we are using the vulnerability curves from the GEM global model in order to assess the probabilistic risk in the city, comparing the different approaches. So as we can see, most of the buildings, it was around 60,000 buildings, if I can remember well, and most of them are masonry buildings. So here we can see the big difference. This is a plot comparing all the different approaches, the 20 different approaches. This is the loss radio, so it's the radio between the losses and the total value of all the builds, and in terms of the return period. So you can see, for example, for 1,000 years in return period, we can see the big difference between all the different possibilities. And we are doing some preliminary analysis. For example, if we compare the different approaches, and for each approaches, the different level of the detail of the VS30. So we can see some interesting things, and probably we can say that for this city, at least, probably the resolution of the VS30 is not the most impacting thing for the risk, and maybe the most important is the methodology, not just the resolution of the data. And we are doing this kind of things like color heat maps with the relationship between, okay, the different kind of buildings and the different methodologies or approach of the side effects in order to see what is the most impacting thing. So for now, some really conclusions, that is, okay, apparently with this really preliminary case, everybody is around the world is very worried about the scale of VS30, but probably the most important thing is not the scale of the VS30, but is the methodology. And there are not many cases exploring the different methodologies and the impacting risk. So for now, thank you, everybody.
Hey, thank you very much. Which questions for Julian, anybody? So Julian, yeah, just a quick one. I'm not familiar with this, so it's going to be naive. But I mean, the different models that you showed for the velocity, side velocity. I mean, it's just based on literature. So I mean, it's a selection of possible models. It's possibly non-exhaustive, I guess.
Yes, we tried to select since the most famous or more used methodologies to more academic approaches in order to see the impact of a big abacus of possibilities. Because it was a very big surprise for me, because okay, I am from the hazard world working now in risk, and in the hazard the side effects is very studied and is very rigorous, but there are not many studies in the risk world about the impact of side effects in risk metrics. So we are trying to do our best with several methodologies, not just the traditional ones, but some more complex in order to see the impact. And the impact looks really, really big for now.
And I don't know, I mean, within the TREAD project, I mean, what do you think is the most relevant, I mean, to what you will do? So in terms of, you know, connecting with other, you know, other PhDs?
So, for example, we are going to estimate the the impact of different approaches. For example, the methodology that Katere and Jared are working in, but we have to testing in terms of the risk, and in sometimes the people is neglecting the effect of the soil, and can be very, very important. So, for example, if we are going to test some examples over the happenings, we have to quantify with this first part what is at least the epistemic uncertainty we are having if we are using a specific approach for the side effects. So we have to test all the different uncertainties.
Okay. All right. Questions, anybody? We're running
I have
out.
a short question.
Yeah, go ahead. Yeah.
You presented some example from Colombia, and I just want to know, will your project run in Central Apennine as well or not?
For now, because our project is about testing the impact of different approaches. So we are, is the reason, okay, we are not testing exactly in the happenings, but we are testing the different approaches with a big abacus of possibilities in order to see the impact of the different methodologies. For example, we hope it doesn't care about the location, but more in the methodologies.
Actually, I want to know, is there any recorded of ground motion from Central Apennine or not? Just it's very important for me that you have some recorded for ground motion in Central Apennine or not?
There is some database, because there are some ground motion models from, I don't know exactly in the Central Apennines, but in Italy there are some microsonation studies in Central Apennines, because since L'Aquila earthquake and since 2016 and 17, the government are founding a lot of microsonation studies in the region. So they have I don't know if they have ground motion records, but they have models about the amplifications.
Okay, thank you.
Okay, so maybe we should go ahead since it's already quite late. So tonight we have the chance to have Fadi from IFP Énergie Nouvelle in Rueil-Malmaison. Is that right? It's in Rueil, yeah. So
Yes.
Paris. And he will give us a talk on critical thinking and I can't remember the whole title now, but you will tell us in any case, Fadi.
Yes. So how do I have the possibility to share, huh?
Yeah, normally you should be able to. Yeah.
Okay, let me do it down directly then. Ah,
There we go.
did you see my screen?
Yeah, yes, we do. Perfect.
Excellent. So here you have the title that you gave me. So,
Right.
so first of all, I'm very happy I followed few of your lectures, and others I checked also on the YouTube. So I'm very happy to be part of you guys. I mean, it's a fantastic project with a very nice, how you say, bouquet of young scientists. So it's a pleasure to be involved. Although my involvement is very small, I would say, but at least I can follow up on your work and on this project. So first of all, I need to little bit introduce myself properly. So my research I'm a sedimentologist by background, so that's to start with. But at IFP since about 20 years, 17, 18 years, IFP is a research institute for energy, a European scale research institute. And so I had to work on other disciplines, not only sedimentology. So that's why my, let's say my work has been on many scales and many disciplines. However, my research interest was always around multi-scale processes in sedimentary basins, fluid rock interaction, diagenesis plus. Why? Because we are now interested in the fluid rock interaction that happens at societal time scale, which means that whenever we think about geothermal energy or whenever we think about using the subsurface, where we could have also some earthquakes or some disturbance in the earth, we can also have fluids that move and fluids that interacts and fluid that can have some impact. And that's why it's important to study. So it's not just the, let's say, the classical geological fluid rock interaction, but it is also with societal interest. And so definitely the application of my work is within the realms of conventional and new energy systems. I'm a Lebanese by origin, and I did my first studies in Beirut. Then I did my PhD in Leuven in Belgium. Then I went back to Lebanon. I worked at the American University of Beirut. Then I came back to IFP. And since then, I'm in IFP. So I have my habilitation in 2015. And since 2019, I occupy a chair for multi-scale fluid rock interaction at the University of Utrecht. Two major, I would say, contribution, other than the papers that I would like to highlight, is a book on the geology of Lebanon that I did in 2014, which is a very, it has a lot of meaning for me, and a book on the multi-scale diagenesis, from which I will show you some of the results that will be a kind of, I would say, eye-opener for the questions of critical thinking. Yeah. So here is the way I would like to present to you, at least to try to be helpful for you, hopefully. First, I want to show you what I do and then give you a little bit of background. Then I would like to look at the reading science, critical thinking, and evaluation. To my opinion, at this stage of your PhDs, I think you already have gone through this. So I mean, you have already been into reading articles, understanding them, and make use of them. So I'm not sure how much the timing is good for you, but maybe it will give you some ideas that you can adopt in your research. So for the background, as I said, I work in the energy applications. So for many years, our energy applications were related to oil and gas, even though with evolution in terms of, let's say, starting to say, well, how can we make sustainable between quotation oil and gas, or how can we clean as much as possible the use of the extraction of oil and the production of oil, and how can we be more efficient and less carbon, I would say, producing. Let's put this aside. With time, we have gathered a lot of information from the oil industry, whether it is data from the subsurface. For example, on this map here, you see in black is the density of wells around the world, and these wells, they could be of let's say 4,000, 5,000 meters in depth, and they bring a lot of information about the subsurface. And also in terms of technology, because the way that we start now, we know how to investigate the subsurface in terms of seismic data and also in the link. The future, well, if we look at the world as a whole, it seems that the oil and gas industry has some decades still to go. But the renewable energy is more and more getting, if you want, getting the place, and hopefully this will help for the planet and for the future of humankind. But anyway, that's the situation already today is like that. So what does it mean? It means that on the top of what is remaining of oil and gas business, there will still be an importance for working on other activities or other application for the subsurface, whether related to resources like water, for example, or minerals, or whether related to storage of CO2 for geological carbon sequestration, or for enhanced or geothermal energy or compressed air and storage of energy. So that's where we are today. And in this case, we have to link also to the surface, because when we have wind energy, for example, or we have hydro energy, or we have solar panels, we'll still need to store energy somewhere. And batteries and lithium are limited. So the subsurface could be a good example to store energy in the future. So with this, if you want a large spectrum, my project, or the project I lead in IFP, called GeoQRS, is, let's say, it takes into account all of this except the oil and gas part. So we would like to try to use the knowledge that we have in order to have a better sustainable usage of the subsurface, meaning application to underground geological storage, geothermal energy, water, and also to monitor and to at least be aware of the risks, whether the risks are associated to the georesource itself, for example, I don't know, pollution of water or decrease of geothermal energy, or to the structure itself, collapse of the well, problems with the structure, or even related to also geohazards, like, for example, induced earthquakes. So what do we do to do that? We work on 3 different clusters. A first cluster is to observe, characterize the complexity of the subsurface. A second one is to understand and control this complexity. I like more the French word for that, which means maîtriser. It's really, we want to understand how to capture, if you want, this complexity. And the cluster 3 is for the modeling. To observe, the best is the natural laboratories, like also your cases and your studies. So we want to work on different rocks, different types of rocks that constitute the subsurface, whether they are carbonate, sandstones, or metamorphic. We study them, we take data from them, and rock samples, let's say, and fluid samples, and we try to mimic the processes in the laboratory, and also to do the modeling. For this, we have a huge amount of technical platforms that we use, from the numerical models, but also from the laboratory equipments and from the field acquisition tools. And we have project partners on the different cases, and one of them that is a very important one is related to my chair in Utrecht University. In this chair, I'm able to go into the project proposals, many of research projects, and also to follow students, master students and PhD students with many applications like hydrogen, sandstone for CCS, for CO2 storage, and carbonate and geothermal. So this made me also with other PhD students that I supervised in IFP, made me think about this question of the project, of the discussion of today, which means how to do critical reading, how to do reading, and why do we need to do reading, scientific reading, and do it in a critical way, and how to evaluate what we read and to make use of what we read. That's a topic that always comes back to the discussion that we have among ourselves and as a team, and also with the students. So to go back to the Utrecht chair on multi-scale fluid rock interactions, so we write proposals that we submit. We are associated to some of the networks like TRED, and that's why I'm here, and also follow up on master's projects. So that's what do I do every day. Now, let me give you a little bit about my background and how the questions of critical judgment, if you want, of the data and the work that we do has some importance. So what I will show you might be far from your fields, but it doesn't matter. What is important is the way things are scientifically, I would say, tackled, and the reasoning behind. Okay, so in the subsurface, the flow properties or the fluid rock systems are associated to at least 3 different end members. There are the facies of the rocks in sedimentary basins, for example, in sedimentary rocks, the facies of the rock, the texture of the rock, which has the initial porosity and pore space. There are also the chemical reaction between fluids and rocks that can make dissolution, for example, make big caverns where the fluids will be accumulated, and fracturing that can be or not related to earthquakes. All of these 3, they will affect what we call the pore space or the reservoir properties, porosity and permeability. Now, the difficulty in this, and this is where the critical way of tackling the research questions, is that we don't know which one takes the lead on the other. Each case has its own subtleties. But at least we know that all of these 3, they are interrelated and they affect the subsurface. The second point is the scale problem. And this scale problem can be in any sort of research. Here I give you an example of a sedimentology study, but it can be also with your data sets. Here I show you, for example, the scale of a seismic section from which we take the faults, we take the different, I would say, intervals, 1 to 10 kilometers length, I would say. And then the outcrop study, which could be a meter to hundreds of meters. And then you go back to the scale of the rock itself, the thin sections, where are talking about micrometers, and even the scanning electron microscopes. Now, in each one of these, there are some complexities. And the difficulty is how to be able to link all these together through the scales. So people have thought about that and a lot about these challenges, and a lot of, let's say, at least facts or factual knowledge is already available. When we look at this, we look at 2 things. We look at representativity of the information or the rock samples here, and also the resolution of that data. For example, if I take cores from a well, I have very high resolution because I can see the rock itself. I can understand every single detail of that rock. So I have a high resolution, as you can see here on Keogh diagram. But at the same time, it represents a very small part or very small volume of the overall sedimentary basin or of the overall population of the data. If we go to the well logs, we lose the resolution a little bit, but we are still, let's say, with a lower amount of the volume. And if we go to the seismic, which has the largest amount of volume, it represents the maximum of the volume of the study case, we have the lowest resolution. So how do people tackle on this? They will use two ways. Either they will go to the outcrop analog to the surface to study different scales, try to bridge the gap of the scales, or even better, they will go to numerical modeling. With numerical modeling, they are capable to take different scales and measure them in different ways. The problem is that when you look at the subsurface, you don't have the same resolution like the outcrop, like I was just saying. Imagine this picture. This is a picture of an outcrop. You see the people are here. It's a picture of an outcrop in Spain. What you see are fractures, faults that are filled with dolomite. It's a mineral. I will talk about it more later. And the carbonate is around. Okay. We suggest that these dolomite, they are more porous. They make water flow better, let's say. And to consolidate our hypothesis in a critical way, we will find caves like this hole here as well on these faults or on these areas that are with the dolomite systematically. So we have a good case. Now, we can study this on the surface like this. We can go everywhere, we can map everything, and we can take samples from everywhere. But imagine that this same structure is in the subsurface, which means I cannot go myself there. It's below the earth. And I have wells. What would be the picture? It would be something like this. Now the question would be, are what I see representative to the original picture? And would I be able to make out of this, let's say, scarce information, what I need to fill the whole picture? This is the challenge that we are facing. And that's why we have to accept the limitation in a very critical way before we go into the model. So the model that I create, if it is made of these information, I must accept that there are some limitations. The other issue related to that and to the modeling itself is that, like I said, I mean, the highest resolution is when I have the rock samples, right? Now, if I have the rock samples, the smallest rock sample will give me results, like here in permeability measurements, that are very varied. I can have from one sample 0.01, one I can 100 millidars. So they will be very different, very diverse results. As I have larger samples, I reduce this variability until I reach a point where I have the most focused, I would say, results. Yeah, but then we are still in less than, I would say, 40 centimeters in length. So I need to link this to the log so that I can, to the well log, so that I can create cells in my model. So those of you who will make modeling, they know that they need to have cells. If it is a 3D model, each cell will have a dimension. So for my dimension in a reservoir or aquifer model, I need to put this information. But if I have fractures, for example, the whole thing will change. If it is an open fracture, I will have much higher permeability or flow of water along this fracture. If it is sealed, I will have it small. Now imagine that all of this information will be in one cell. So in one cell in the model, I have to take into account all of this information, because there might be some open fracture, there might be some closed fracture, there might be some different variability of the results of the permeability. And all of this information must become one value by type of parameter that I'm looking at for 100 by 100 meters, if you want, in dimension. So these are problems that we have to face. So we do have a lot of state-of-art technologies and techniques, and we use them, these methods. And all of these methods, from the field work to the chemistry to the petrography, they have their own limitation. One of the most important limitation is size, because as I can study the rock in the mountain, like I showed you, I cannot bring it to the lab. I will have to bring some samples, and then from these samples, I will make synsection, or I will study the chemistry, and so on and so on. And I will go down and down and down in the dimension. But at the end of the day, I can make a concept, and I can prove that my concept is in harmony with the data that I have gathered from the case study. So if I go now a step backward, every sedimentary basin has to have an initial mineralogy composition and deposition. It will be buried. It will be also affected to a fluid rock system at very large scale that will create with fracture a lot of processes, dissolution, cementation, that will change the mineralogy of the rock. And what I need at the end is to understand all of these processes so that I can come up with a concept model and a numerical model for the reservoir evolution at larger scale, but at a reservoir scale. Then if I look at the larger scale, I need, with all the numerical tools that we have, I need to consider the deep earth processes, because the subsidence of the sedimentary basins, for example, and their deformation are also related with the deep earth processes. And if I want to make sure that the numerical model of the smallest, I would say, aquifer or reservoir model for the fluid flow, I need to confront it with natural laboratory, natural examples. So observe, control, and model. Observe has its own limitations, because how do I take all of this information and make out of it a meaningful understanding? Control, I need to quantify, which is not easy at the different scales, and create a concept model. And model, when I model, I have to take into account whether I'm modeling what are the attributes that I want to simulate, at what scales, and what technologies to use. So basically, the loop that is a little bit used everywhere is to have a conceptual model that is based on the data that you have, quantify, and use this quantification to make a numerical simulation to answer a certain question. And then once you answer the certain question, you confront it with your conceptual model and you say, well, is the conceptual model correct or not? Or how can I improve it? And then you continue to iterate in this manner. So let me give you an example of one of these problems in critical thinking, or at least in that I somehow dig the past and get it out for you from my own career, let's say. My PhD, more than 20 years ago, was on dolomitization. Dolomitization, or dolomite, dolomitization is the formation of the mineral dolomite by direct precipitation or replacement from calcite and aragonite. Maybe some of you know the Dolomite Massif in Italy, and maybe you have skied there and so on. So it's a huge area with dolomite, with these rocks. The question is how these dolomites form. Dolomitization is a secondary mineralogy. It means that at the time of sedimentation in sedimentary environments, I would say, the rock is calcite or aragonite, if you want, carbonate. And it is changed to become a dolomite either by adding magnesium to the calcium carbonate, like you see in the first chemical reaction here, to create CaMgCO3. This is the dolomite mineral. Or simply, if you have calcium in the water, you add magnesium and CO3 and you create CaMgCO3, which is the dolomite. So chemically speaking, it should not be a complicated issue. Yet, the dolomitization is a problem because today we don't see dolomite in the sea. Although there is a lot of magnesium, a lot of calcium, we don't see, let's say, dolomite precipitating in front of us. It's very difficult to synthesize dolomite in the lab. To do this equation that I showed you, it's very difficult to let them kick off, if you want, in the laboratory at lower temperature. And also, there are a huge amount of dolomite everywhere in the world, like in the Italian Massif, and we don't know how it works. So what people used to do is that, or researchers, like when I was at my PhD, I would say time, is to follow the bandwagon. What does it mean following the bandwagon, or what is the bandwagon effect? It means that you think about something, but at the same time of your work, there is a kind of a general truth, or people follow a general way of explaining something. So what you will do at the end, you will say, okay, I will not fight everybody. I will follow the trend. I will jump on this wagon and go with the train. So the dolomitization was explained with different models. In 1959, the model of dolomitization was burial, which means the carbonates, when they are buried, they get dolomitized. Everybody, hundreds of papers will be written and will explain the dolomite as being a burial through the burial model. In the 1960s, somebody came and said, no, burial is not the best way to explain the dolomitization. There is another way. If water is refluxed into the subsurface, they can create dolomite. Then sabkha, then dorak, then reflux visited again, then etc., seawater, then hydrothermal. So a lot of ideas came, and every time one idea will come, everybody will follow this idea. This is what we call a bandwagon at that time. So at my time in 2000, 2001, 2002, the most accepted idea was that all dolomites are made by hydrothermal fluids, hot fluids that will create dolomite, or will make dolomite. So these are some of the models: evaporation, etc., and burial, all of these. These are all published, and many papers follow this. And so if you look at the concept itself, you will see that the situation is not so complex. If you have a lot of magnesium, you dump the magnesium with calcium, and you will get dolomite. So what do you need? You need a supply for the magnesium from seawater, from hypersaline, from high magnesium calcite, you need a permeability, faults, fractures, and you need time. And so if you combine the hydrology and the models, then you can understand how the dolomite form. So I took this during my PhD as a starting point. And I found out that in reality, I can have two models of dolomitization at the same time. I don't have to follow the bandwagon and take it only from one side. I can have multiple dolomite models together. So I published my work at that time, and it was really the highlight of my PhD, where I would say we do have a reflux dolomitization in a first step, but since we have fractures and faults, and we can have also hydrothermal fluids, then we will be able also to create a second or a mixed hydrothermal and reflux, or hydrothermal and evaporative dolomitization model. And I remember at that time that when I came to my professor and I said to him, well, I would like to go for a double dolomitization process. And he said to me, why do you want to do that? Either stick to a one model or to the other. Why do you want to put them together? And I said, because I think it makes a better meaning. It's more meaningful. And that's what I observed from the data that I have. And indeed, it was probably one of the best papers I had. So with that now, I would like to look a little bit with you on how to read science and how to look for the critical thinking in what you read. It's like I said, I am not a specialist in reading science or critical thinking, but I try to do the best I can to be helpful for you. So if I go back to the context of PhD in my institute, or how most of the PhDs that I have already supervised, how do we split, if you want? How do we organize? Usually on a PhD for us is a 3 years project, and it has to be to provide a solution, of course, an original, a new solution for a scientific question. So in these 3 years, we start with a literature review, synthesis on the literature review. Then we have a field work, or since it's a sedimentology, we look at the rocks, at the data from wells or from the outcrops. And then the student will have a mid-thesis exam in the middle, or it's not really an exam, it's more like a presentation and a report. Then first or second article, because sometimes a first article comes before the mid-thesis exam or the mid-thesis milestone. Second fieldwork campaign, a possible one, and then another article and the writing up of the thesis from the last 6 months. So first 6 months for literature review, last 6 months for writing up the thesis, and then participation at congresses, whether internal, national or international. Now, what I want to tell here is more related to the literature review, of course, because it has to do with the reading. The literature review is a very important part, and for the first 6 months of the student has to read a lot of papers. Now, when we say literature review, again, the French, I don't want to look like biased for French language, but the French way of explaining it suits me better, is a synthesis, not just a review. The student need to synthesize the material read, the literature, the articles, the papers, the text in the books, etc. He or she needs to synthesize them in order to answer or to use them for the question that they set at the beginning of their or set by their PhD. It's not the same. It means that you can read, I don't know, 100 papers, summarize the 100 paper. Fine, that's very good. But that will not help. What will help is to synthesize or to take out of these papers the information you need to answer or to tackle the problem that is at hand. And within this literature review, you look at previous work, at the concept, but also at methods and also at data. Because in your research, in your manuscript, you need to provide a chapter on previous work, a chapter on methodology and data. So the student needs to show that these methodologies as well has been well understood, and their limitations, especially if you want to go into a critical thinking of your own results, you need to be able to know what are the limitations on the methods that you followed, whether they are numerical codes, whether they are experimental, and so on. So all of this is the basis, the real foundation of a PhD project. And if you look at it in a kind of weight of how much work needs to be done, the reading science that has to be done in the literature review, synthèse bibliographique, etc., and even when you are finishing up your thesis at the end, or even when you are writing your articles, is in this way. So a lot in the beginning and a lot at the end, actually. And of course, this is a very simplified way, because you can have, you will need to read a little bit more when you are writing your articles. Now the question is how to do that and why. So the premise here is to say irrespectively of what I showed you here, reading science should be something that has to be done all the time. And the question would be, why should this be done? Even beyond the PhD. As a scientist, you need to read a lot, and we read a lot. First, we have to understand that the articles, the scientific articles, are the language and the content with which we communicate between each others at the international community. So we need to read and read well, because we need to be able to get involved in the conversation in our discipline. How are you going to discuss with another, I would say, I don't know, sedimentologist in another place in the world if you don't know the language of your discipline? And we need to read because we need to learn about the research that is being done before your work. Many times we get the surprise that what we want to do has already been done. So wouldn't be not logic to take this into account and to change the course of your work? It will be a pity if we don't read well and we reach the end of the work to discover that it has been done or that it can be improved in a better way. So that's why you need to read, to question your own work and to improve your work. And you can read through textbooks, through websites, through YouTube, through all the possible popular sources that you can imagine. But the scholar articles are the must because they are the ones that have been reviewed by peer scientists, and they went through the process of scientific publication, which means reviewing with editorial board and so on and so on. So you know that this this article went through all these steps. So let's go now directly into how to read and how to make the most or effective ones. Now, these are my ideas that I also took from different sources, but I do not want to say that you have to do it this way. No, you have to do the way that you like, the way that you think is the best. But this is a way that looks to me interesting, at least to me, and I would like to share it with you. So the first thing to do, actually, when I take a paper, when I find a paper and I want to read, the first thing I do, I don't start to read from the beginning straight on. I try to see what are the points that are of interest for me. And these points of interest for me to decide whether I will, let's say, download or save this article or not, are either in the title or in the abstract or in the keywords or in the figures or in the first and last sentences of the introduction. And I will show you an example. And always I try to see, because I want to, if I'm interested in what those people have done, you can also search for sentences where you have like, we propose, we construct, we suggest this model, our study, something like this. These are very practical issues, but they will help a lot because then you don't have to waste a lot of time. Give you an example from my own paper that I just showed you before. So the title is Reflux Stratabound Dolostone and Hydrothermal Volcanism Associated Dolostone, a two-stage dolomitization model. Fine. From the title, I know that this is a mixing of two models of dolomitization. One is reflux, one is hydrothermal. If this title doesn't interest me, there will be no go. I don't continue. And then look at the way the papers are written. In the first paragraph of the introduction, various dolomitization models have been proposed to date, covering many diagenesis environment and involving fluids with wide range of chemical composition, reflux, subca, mixing, etc., etc., all the models. Yet the enigma of dolomite is far from being universally solved. At least 4 major questions remain subject to debate: kinetics, thermodynamic, geometry, etc. So now I know that in this paper, if you want, the scope of the research is on that. If I'm interested in this, then I continue. If not, no go, I stop. And then in the last part of the introduction, usually the writer, the author, will write what they are going to do, what to expect in the paper. Here, what do I expect in the paper? Taking into account the major problem of dolomization process and the perspective of these dolomite, this paper discussed this paper, like I suggest, like I propose, two genetically distinct but intermixed dolostones, strata bound and volcanism associated dolomite. Voila, it's there in front of me. In addition, this paper invokes dolomization by means of distinct mechanism. Comparatively, many dolomite are exposed today could be the result of several rather than a single mechanism of dolomization. That's the applicability. And if I want, if this makes me a little bit interested about the paper, then I go check the figures. And I will check, of course, the figure of the model that explain what I just read. Then I say, okay, I would like to read this paper because I will find information that will help me for my research in that paper. And that's how I start to read the paper. Now, when you read the article, usually all the scientific articles are the same in terms of structure. You have an abstract, then an introduction, methods, result, discussion, and conclusion, right? So there are two things that from my experience with my students, especially, I understood. The first thing is that the students, they will complain. They will say, oh, we don't need to, we are not interested in reading a lot. It takes a lot of time. I prefer to do some experiments. I prefer to go chase data, etc., etc. It's true. Let us accept this idea. If I come and I say to my student, look, I have a database of articles of 1,000 or 800 articles on dolomite. Take them and do your literature review. This will be like torturing, of course. So you need not to read a lot and many things and get overwhelmed with the papers. It has to be made in an intelligent way, in a meaningful way. And usually the start to finish reading is not the best way. It means that if you have an article, maybe it's not the best way that you read the whole article from the beginning to the end, probably. Again, these are my ideas that I propose, and I'm not saying that you need to do it this way. Telling you how I would see it better. So to do effective readings, let's look at these three rules. First, follow an effective order of reading. Here, I suggest, not me, but based on what I have also read and seen everywhere elsewhere, to start first, like I said, with the title, etc., just to decide on keeping the paper or not. Once you keep the paper, start to read the abstract. The abstract has the full juice of that paper. Once you read the abstract, you ask yourself, is this article relevant to my research? Is this what I need? Is it now that I need this to read this? If yes, then you go to the discussion. Why? Because you will see later, the discussion has a lot of information that you need. And then the introduction, and then the results, and then the methods. Now, if you are interested only in the methods, why not going directly to the methods, right? So you have to make it on your own. You have to make a sort of rules to how you want to read. And try to get if you want the cream of the paper in terms of finding, but always question what is relevant to you. Like I said, we are doing a synthesis. We are not just making a summary of paper. You are not a librarian and you want to make sheets of summary of paper so that people can come and read. You want to read and make a synthesis of that paper into the question, the scientific question of your PhD. So in the abstract, you will get the purpose, the why, the methodology, the how, the results, the findings, and the conclusion. So actually, the abstract is the starting point. So is it relevant to your work? Yes or not. If not, you stop. If yes, you go to the discussion. In the discussion, you will get answers to the question posed by the authors, and the explanation on how the results will support the conclusion. Here you have to think, is it appropriate? Is it clear? Is it robust? Do you agree? Or is it not so well argumented. Again, if no, you stop. If yes, you go to the introduction. Why? Because then you will get the right interest and the larger context of this study. You do the same exercise and you go to the results. Here you have the finding, you have the data, because if the steps before are not good, why do you want to look at the findings and the data from the beginning? And then you go to the methods at the end, if the data are appropriate and they are well supportive. But then again, I said to you, this is an example. So in order to read well, you need to write well as well. You need to take notes. So this is what we call active reading. Active reading is reading, and always you ask yourself, do you understand? And if you understand, you take the notes. And I will explain this more in details after. So organize your thought, make a strategy, make a read order of your articles, define the main points, and then write down your effective notes. You can make a template for the effective notes as well, or make a kind of organized way. So for reading science, what are the few practical suggestions? First, a very practical one, you need to plan specific hours for reading sessions. You need to say, well, I don't know, in this week, every week I will give an afternoon for reading, let's say. Prepare the reading sessions. You need to prepare the articles, print them maybe, or put them or save them. Provide note templates if you want to make a note templates. Maybe you provide also pencils, highlighter, prepare yourself. This is important psychologically because you are preparing yourself to go into a session of reading. Read actively and take effective notes. Read actively, it means that when you are reading the sentences, you understand what you read. If you don't understand, you stop and you try to understand before you continue. And it will help a lot if you take notes. After that, what turned to be very, very, very productive in my group was always to explain and to discuss the articles, not to discuss the articles as a presentation, not to ask the student, come this day, you will come and you will make a presentation to explain to me the article. No, discuss the articles on a coffee, on a coffee break, without figures, without slide, just telling what you understood or what is your take from that article. That's the important thing. What are your interests in the finding? What can you do with that? And maybe search for references or for sources and go to read more and more. That's the plan. So again, if I go back to this active reading, it means that you want to understand. You want to relate the ideas to previous experience. You want to link concepts to the experience. You want to connect the evidence to make the conclusion. And to do this, there are four steps that a strategy for 4 steps. First, like I said, the active means clear, intentional, focused. 2, to answer critical questions, active reading and answer your own question. So first, when I say clear, intentional, focus, it means that you need to ask yourself the most important question. To what extent does this article help me understand what? I'm interested in a dolomite. Is this article, from the title even, will help me to understand a question that I want to deal with for my PhD? That's why you are reading this article. And why you are not reading this article. What is the relevance to your work? What is its purpose? So you have to build your own strategy. Second, you need to answer the critical questions like, what are the implications of applying these ideas in this text? Once you read it, once you saw that there's it's important for your work, you ask yourself, what will be the implication? What will I do better in my research? How valuable is this text for doing that, doing this, etc.? Where does this text situate with respect to other literature in this theme? And you keep asking yourself, if you understand, summarize, synthesize on a sheet of paper, a summary sentence or a pitch of what the text says to you. I used to write myself, and when I used to read the papers, I write on the paper itself a sort of a pitch. Very important to do this, to do that, so that I can keep it. Now, these summaries, if you are well organized, can be used later on for your manuscript, because you can say in this paper you have already a pitch that you can add in your when you write your manuscript or your article. So at the end, you will go back to your first question about why it's important and how can this article help you, and you will have more precise information. This will help me because it will explain to me this and that, but it doesn't answer this question that I have to find it in another paper. And when you write these sentences, you can use them in your writing yourself. So a few practical suggestion here is writing, note taking with reading. You cannot read if you don't take note. It will not. I mean, maybe some people have the gift of memorizing what they want to what they have in mind, but writing is always important. Ask questions, validate and judge the text, prepare answers and sentences to fit in your manuscript so that you don't lose time, and incorporate the new ideas in your work. So what then is critical thinking itself? By definition, critical thinking is the systematic evaluation of the arguments, the idea, and theories of others. The basic premise of critical thinking involves asking critical questions. So that's what we have been doing so far, to form an educated opinion of whether or not those resources are credible. But you want to go further than that, and we will see that in a moment. So you ask questions, you want to know if it is okay, if it is, let's say, meaningful, if it is credible, right? There are two ways in thinking styles. Either the sponge thinking style, which means we absorb as much as information as possible. We don't want to discuss if it is trustworthy or not, reject or not reject. Or panning for gold thinking style, where you inspect, you examine, you ask critical questions, you challenge, and you try to repeat the reproducibility. And something I found that was very interesting is the Bloom's taxonomy, which explains a little bit more this type of thinking styles. Remembering, understanding, and applying would be the low order thinking style, which is a sponge style. And the higher order of thinking would be analyzing, evaluating, and creating. Now, what does it mean? It means when I analyze, I break the information into separate components, because maybe in that paper, this information that I have is not all of it important for me. I am interested in some parts of it. To understand the assumption, the argumentation, and limitations, and especially the relevancy. These are like when you ask questions like why, how, and what if. When you evaluate, you judge, you assess, you criticize the information. Will this be good for me? Would I take it? Is it correct? Is it robust enough? In the eye of my question to solve in my research. So these are the questions like so what and what next. And then once you go further, you can combine the elements, at least that you have selected, and you produce new original work, original ideas, acquire inventiveness and originality to form new ideas. Because I mean, I don't believe that you can invent new ideas like this, like, you know, you are walking in the street and you invent ideas. No, your invention is based on what you have already digested from the analyzing, evaluating, etc. And there you ask yourself, how can we improve what you know? How can we change? How can we adapt? So if a practical suggestion for that part then of critical thinking is follow the analyze, evaluate, create approach. It will help. Question the text and your own plans. You read the text and you have already in mind what you want to do, right? So question this text. Is it robust? Is it good? And then question your own plans with respect to what you read. Discuss the papers with your colleagues. Again, this is very important, to discuss the papers with others. or your ideas with others. Engage in debates, be courageous. Some people will be afraid. I know a lot of my students, they were afraid to share. And they would say, what if they take my idea, let's say? But if you are good enough and fast enough, nobody will be faster than you, right? That was usually my response. But more than that, you have to be courageous to debate, to discuss, because you might get an answer that doesn't that you are not ready to take. Huh? You don't want to know that probably you are wrong, yeah, or probably that you can make it better or improve your work. So that leads us to the end with the evaluation, where you have to evaluate, I mean, reading, science, critical thinking, and evaluation. So you have to evaluate a little bit what you have done. And this process is something that is continuous. Again, it's continuous through a PhD, but it's continuous through your scholar, I would say, life. 5 suggestions that I found very interesting, and that's from a BBC sort of TED, if you want. First is to accept the confirmation bias. What is the confirmation bias? Is where you have, for example, if you put a 6, if you write a 6 on the floor, and you are facing somebody, the somebody in front of you will read it 9, and you will read it 6, right? So it's the same, but if you are looking from a different angle, you will see it in a different way. So the relative interpretation may exist, and you have to accept this. And you have to make use of it for your own purpose. And accept the complexity and the nuance. We say the sky is blue, but blue is not blue, right? You can have dark blue, you can have different shades of blue, etc. And this is also because there are some limitations that we need to accept. Practice the intellectual immunity and empathy, which means that if you're working on something and you have some results, you can accept that maybe you are wrong. There is a possibility that you are not 100% correct. And accept also to have empathy towards those who are telling you that your work is not as good as it should be, let's say, or that they have another way to tackle your question, by putting yourself in their shoes before trying to be on the defensive. Check your sources always. This is the scientific methodology. And the sources can be today a very good, let's say, but maybe in the future they will find out that they are not as good as we thought of. And avoid the misjudgment and bandwagon effects. Avoid to say, okay, if everybody is saying this is like that, then let's follow this trend. Even within your own group of research, even within your professor, if you are in a positively, in a critical thinking, you can ask why not in a different way. And at the same time, do not oppose just because of the person. Do not say, okay, I don't want to follow this idea because it is championed by that person, just like that. So these are important suggestions that will help to evaluate the steps to take. But in general, if I now conclude on the whole thing, so development of the critical thinking and evaluation for reading science, again, this is in a lifetime of PhD, but I apply it until now, these things. So it's not only for the PhD. It is a continuous process. So you have the research, you have the learning, managing knowledge, testing knowledge, applying knowledge, and communicating the knowledge, right? In the research part, you do the skills. You build up your skills, your capabilities. You work in the field, you work in the lab, you work behind the computer, you make analysis of data. All of this is building up your skills. And then in order to learn, the best way is to teach. In order to learn something, the best way is to come and say, okay, let me explain it to somebody. Because when you explain it to somebody, you will understand what you don't know and what you should know. And then you need to do a lot of organization. Organization is important. Like I said before, if you don't write, if you don't take notes, then how can you read well? You need to organize. You need to organize the data that you are consulting. You need to organize the data that you are producing. And you need to be able to explain your data, explain the process, explain how you got your results. And then once you can explain, when you are well organized, when you know how to teach what you have done, then you can be confident of your problem solving and the application of the knowledge that you acquired. And then the best way is to share it with the community. And that's where the communication comes. So from one side, you have to ask about the meaningfulness of the data, of the skills, of the studies, of the learning, the significance and their impact. What will be the significance on you, on your project, on your work, on your research, on your career? What are their representativity? Like I said, even in the work on sedimentology. So I have a small population of data, and I want to say that these are representative of the whole process everywhere in the world. So what I'm studying in, I don't know, Nicaragua will apply to China. How can I prove this? This is very important. And how can you, is it reproducible? Can you prove that you can reproduce the same process, the same numerical simulation and get the same results? And if yes, would it be applicable? And to what perimeter, to what scope? So here I also refer to the Feynman learning technique. I liked it as well. It's again the story that if you want to learn something very well, you need to teach it, or you need to explaining to somebody, and then you will understand what's missing, right? And so at the end, if you want to communicate your study, you have to ask yourself, are your results accessible enough to everybody? Can they understand? Because even if they are true, even if they are robust, even they are the best science ever, if the audience cannot understand what you are explaining, then you have a problem, right? If you don't have the accessibility to share this data, are they useful for them? I have seen many brilliant research, and then I ask at the end, or somebody will ask, but what are we going to do with that? And then the question of how much we can still improve, because if you show that there are still some improvement, then you engage people with you. Then you will have people who will come and say, we are interested to work with you. We are interested to go further. And that's the start of a new chapter. Voila. Thank you very much. So I finished.
Thank you very much. I think David is not with us anymore. Yeah.
No, David left, but yeah. Questions, I guess there are many questions from the students. Thank you for the great presentation. Questions?
Yes. If you have some comments as well, I'm happy to take, because like I said, I mean, it's not something something so how we say so new to you, I think.
No, actually, it's nothing new. And I think that we are all experiencing somehow the feeling of being a bit overwhelmed by literature and by papers, because I guess that we are all facing new challenges. We are all in new projects, so we have many things to learn. So of course, reading is a very big part of our work, at least now. So it was very interesting to attend this lecture, and yeah, it would be good to have a more clear plan to follow when you need to start reading something.
Thank you. Yeah. Yes, I think that it's not easy. I know I faced it myself. I have experienced this with the students that I supervised. It's not, and I remember, for example, one of my students had a visit of a geological survey, and the colleague in the geological survey gave him 1,500 papers. These are all the data that we have on, I don't know, let's say this geological formation. And it was counterproductive. It was counterproductive because first of all, the poor student got shocked what to do with all this information. And then every time you want to find something, you have to go. Of course, now you may say there is virtual, no, there is artificial intelligence and stuff like that. Maybe it can help to dig some information. But still, you need to make your own judgment. You cannot rely on artificial intelligence. So I think that it looks quite naive, but that's the reality. You need to organize your time. You need to reorganize yourself. You need to give some space for yourself. You know, like for example, when you say, "I want to go and have and watch a nice movie," yeah. You give yourself time, no? You say, this day on Wednesday, we are going out to the movies, and you watch a movie. So you need to do something like that. You need to say every week on Friday, let's say, from 3 p.m. to 5 p.m., I dedicate this time to reading. And then you read. And it will be much better if you can also add to this a sort of, you know, after that, I don't know, a beer pause or a coffee pause with your friends, your colleagues, and then you talk about what you have read. Hey, I found this article is fantastic. Look, these people, what they have done verbally, without, you know, looking at figures and diagrams and going into the details. Just this way, it will make a sort of incentive.
I think apart from the challenge that comes with trying to understand papers quickly, since we have so many to process, I think after that, it reaches a point where you've read so many that you're not sure if you even remember what you've read from the beginning. So I think from my part, I guess that's where I struggled then in organizing and trying to remember how they're organized, I guess.
Yeah. So I saw this problem as well with some of my students, and it looks more due to digital reading, which means that when you read papers on your screen, you don't necessarily take notes, and you read it and then you will forget. Even if you take some note on a paper, then you lose the paper and so on. The old school, it seems to me better, which means that you print the paper and you write your comments on the paper, and you put this paper that you read. I still have, for instance, my PhD folders with papers and the notes on them. And when I write my manuscript or even my papers, I go back to these papers that are so old now, and I check what I wrote as sentences, which I can include in the paper itself. So this is the old school. Now you are young and you are much better and more important, you know better how to do things now. So maybe you can do something similar digitally as well. Maybe you can, I don't know, make a, I know that there's a EndNote or OneNote, or there are some softwares you can use where you can add to your paper that are also used for referencing some comments, some sentences, and therefore you can copy these sentences when you need to write your manuscript. Yeah, because it's very, very important when you want to write something at a certain moment. you don't fall in what you said just now, which means that I want to write, I have read so many papers, and now I lost the track. I don't know where to get this information. So if you have a sort of organized way to read and to take note, that's what in this lecture is called effective note-taking, then you can get this information that is written. And this will help you because it will take out the nightmare that you will forget, because you've already written them and they are there. So,
Okay, so if there are no other questions, we can conclude this session of today. And thank you again, the speaker, for the super interesting presentation. And I wish you a good evening. And yeah, see you with the students in a couple of weeks, I think. But you will get plenty of emails, don't worry, and reminders.
okay, thank you very
Thank
much.
you.
Bye-bye.
Thank you
Bye.
very much.
Thank you. Bye, everyone.